In a previous episode, I unveiled this inverted pendulum kit and used it to demonstrate some important control theory concepts. In particular, I tuned a PID controller so that it would balance with the beam pointing up. My goal is to eventually train an AI to do that for me, but let's start with a slightly simpler task. Can I get a reinforcement learning agent to learn how to swing the pendulum up from a resting position to land nicely at the top? From there, I want to see if I can move the agent over to a microcontroller so that it can run without support from my laptop. While training on a microcontroller is probably out of the question, most agents in deep reinforcement learning are fairly simple neural networks. It should run on a beefy microcontroller without a problem. In theory. I'll use one of the new ESP32S3 boards, as they're quite powerful and offer some AI hardware acceleration. Let's get started. This is the ST Eval EDU Kit 01 from ST Microelectronics. It's a simple bent aluminum rod attached to a rotary encoder, which itself is attached to a stepper motor encased in an acrylic tower. The rod can rotate around the encoder's axis, while the stepper motor can move the encoder around a vertical axis. The idea is to create a program, or AI in my case, that can swing up the pendulum and ideally balance it at the top. The first thing I want to do is get rid of the STM32 board. I have nothing against it. It's a great board, but it's limited to 84 MHz and 96 kilobytes of RAM, and it doesn't offer any neural network acceleration. It might work, but I want to work with something beefier to get that latency down. So I switched to an ESP32. Specifically, I'm using the Seed Studio Xiao ESP32S3 board. It has an Extensa LX7 dual-core processor running at 240 MHz and 8 MB of RAM. Yeah, this thing is a monster. Oh, and it has special AI acceleration built into the hardware that can use the new ESP-DL framework to speed up neural network calculations. I paired it with a DRV8825 stepper motor driver from Pendulum. This should make controlling the motor a little easier, as it just has direction and step pins. There are also Arduino libraries to handle much of that for me. For these types of research projects, I like making my life easier. Getting rid of the ST electronics meant getting rid of the nice 12-volt plug on the stepper motor board. I also felt that 12 volts was a little underpowered for this motor, so I bumped that up to 18 volts with this power brick. And then I noticed something a little odd. The driver board and stepper motor got hot. Like, really hot. The screws holding the motor in place started melting the acrylic. I'm gonna go with not ideal if I wanted to run this project overnight. Even having a fire extinguisher nearby wasn't enough to comfort me, so a few modifications were in order. The first was to cut some holes in the acrylic around the stepper motor to allow for better airflow, or, any at all. Even Pippin expressed concern for all that heat buildup. A couple of 40mm fans and a heatsink on the bottom of the stepper did the trick. Temperatures now ran in the 30s rather than the 70s, and this is Celsius. I can rest a little easier knowing the acrylic probably won't melt or start a fire. The driver board also ran super hot, even with a heatsink. A simple fan did wonders here. And the LEDs promised to help the AI learn faster. That's how that works, right? With all the heat issues taken care of, I could finally turn my attention to the AI side of things. Since the microcontroller is a poor fit for training an AI model, we'll need to do the learning on a computer. The first bit of code I needed was something to read from the encoder and control the stepper motor. This Arduino code accepts JSON messages over serial, moves the stepper motor by some given amount, and returns with the position of the encoder and stepper in degrees. It's a simple interface that we can then wrap in our learning environment. We'll be using reinforcement learning to train an AI to swing up the pendulum. In reinforcement learning, our environment is the world, or virtual world. that we wish our agent to interface with. We use an interpreter to derive observations from this environment. In our case, these observations will consist of the angle and angular velocity of the encoder, as well as the angle and angular velocity of the stepper motor. Our agent, the AI portion, will take in these observations and predict an action to perform. In this case, our Python program will communicate over USB to tell our Arduino how to move the stepper motor. Ideally, we will deploy this agent to the Arduino so that the take observation, make a decision, and take action loop is much faster, and we can do it without requiring a powerful processor or GPU. But for now, we need that GPU to train the agent. To assist with the training, we also introduce a reward feedback system. Our interpreter will provide this reward based on what happens in the environment. The agent will update its internal weights based on this feedback and a history of the actions and observations taken. I highly recommend checking out my Introduction to Reinforcement Learning video if you would like to dive more into the details of how this works. I'll make sure there's a link to it in the description. Here's how the reward was initially determined. It was inspired by the inverted pendulum environment from the Farama gymnasium framework. The idea is that the angle of the pendulum as it rotates around the encoder would be normalized between -1 and +1, with 0 being the pendulum in the upright position. -1 would be -180 degrees and +1 would be +180 degrees. At each step, the value of the encoder angle would be squared and multiplied by 1. So the farther the pendulum moved away from the upright position, the larger this value would be, and negative values held the same weight as positive values. Similarly, we would take the square of the angular velocity, but we'd multiply it by 0.01 so that it would not be as important as just the angle. This is to encourage the agent to not swing the pendulum around quickly. We apply the same calculations to the stepper's angle to encourage the stepper motor to stay as close as possible to the original starting angle, which we set as 0. Once again, 180 degrees is normalized to +1 and -180 degrees is normalized to -1. However, note that the constants are much lower for the stepper angle phi and its corresponding velocity. That's because this is more of a general encouragement. The encoder angle with the pendulum should be the greater incentivizing factor. Note the negative sign here. A perfect score is 0, and that's if the pendulum is in the upright position, the stepper is in its starting position, and neither encoder nor stepper is actively moving. We know that's impossible, but this reward function will encourage the agent to try to get as close to that state as soon as possible. There's one more caveat here. If the stepper motor goes past 180 degrees in either direction, we'll give a 500-point penalty and end the episode. This is a hard boundary, as we do not want the encoder cable getting tangled up, so we'll strongly encourage the agent to learn what it needs to do in a 360-degree arc of the stepper motor. Now, let's see what our agent looks like. As it turns out, the agent is a very simple 3-layer neural network. The 4 observations are fed into the first layer, which has 256 nodes. A hyperbolic tangent function is used as the default activation function. We'll want to change this to the rectified linear unit as that's easier to compute, especially for our microcontroller. The next layer is also 256 nodes, followed by an activation function. The last layer is used as a regression function. The single output is trained to predict how many degrees to move the pendulum based on the observation given. The left side of this diagram is what's known as the value network. It helps predict the expected value of the agent being in a particular state given some set of inputs. It's only used for training, so we can honestly get rid of this entire neural network on the left side when we go to deploy this agent to a microcontroller. Because reinforcement learning is so sensitive to hyperparameters, we'll need to do hyperparameter optimization. We'll use Bayesian optimization with Meta's AX framework. This is something I covered in the previous episode, so I highly recommend checking that out if you want more details on it. In our Jupyter notebook, we're going to do the training in hyperparameter optimization. To start, let's import some packages that will help us do all of those things. We will configure some settings here, and then we're going to try to connect to our Arduino board. First, we'll try some basic communication, see if we can move the motor a little bit. Looks good. And we're going to do a couple of more tests, make sure it can move around. Let's do a stress test. Should move back and forth a whole bunch. Please don't whip the camera. All right. With that done, let's move it back home. I'm going to move it back so it doesn't tangle up the cord here. We'll close those communications, and let's do a basic step test. There it goes. That looks good. We'll log into weights and biases. If you watched the previous episode, you'll know what that's for. And let's define a few helper functions. Make sure we can draw from our action space anything between about 1 and -1 or -1 to 1, and those get multiplied by 60. I believe if I zoom up, I can verify that. And that is, here it is, the step or action multiplier. So -1 is -30, 1 is +30. So it's a 60-degree arc that it's capable of moving in. So we'll build the environment, and now we need to test that environment to make sure that the gymnasium wraps our communications appropriately. Test the encoder. You should all say -1 or 1, depending. 0.5, that's not right. That means I need to reset my connection. So as soon as that ends, I'm going to reset the connection to the Arduino. So I'm just going to unplug it and plug it back in again, because this should not be 0.5. All right, let's reconnect. Test the encoder. Give it just a second. There we go, -1. That's pointing straight down. And now when I move it, it should be 0 at the top, -0.5. Good enough. And let's run some random steps to see what happens. Yeah, that looks pretty good. Try running the environment for a few steps. It's going to move some. That looks good. Reset our environment. Oh, this is checking the rewards. Not really worried about that. Now we're going to test the timeout. And this should just move it back and forth a bunch, and it should go for about 30 seconds. So, all right. So the episode timed out, and then we're going to run the gymnasium, or excuse me, the Stable Baselines environment checker, where we pass it the gymnasium environment, and it goes through some methods to make sure it can appropriately communicate with that environment. And the stepper motor is going to move a little bit, seemingly randomly, and the check is done. I got no error messages. Let's close that environment. Now we're going to define our tests. All right, so a few of those. We have our project settings. We're going to name this project HBO test, and that's fine for an experiment name. Actually, let's make that 2, because I was working on it earlier. And we're going to set our hyperparameters. This is kind of based on the inverted pendulum problem from the last episode. So we're going to start with those and see if Axe can help us find good hyperparameters. We'll create our environment. We will construct our backup file for Axe, creating experiment, excellent. And now we're going to let this train, which might take days. And so I'm going to bring up weights and biases. Let's go to this project. And this is the wrong one. That's actually from the previous episode. We'll refresh weights and biases to see if, oh, there it is, HBO test. Let's go there. And we'll wait for these metrics to start filling in. When I let the script run for a few days, I noticed that the agent was struggling to learn. It just kept doing stuff like this. Each of these lines is a single trial, where I let the agent train for 100,000 steps. The ACTS framework then selects new hyperparameters, and the training process begins again from the start. Ideally, we want to see the agent improving as we start getting better hyperparameters. But that's not what I'm seeing here. The agent never really catches on. I also noticed that the average step time is pretty high. It can be between around 20 to 50 milliseconds. In my experience, this latency needs to be less than around 20 to 30 milliseconds for an algorithm to be able to respond fast enough to balance the inverted pendulum. So that's also going to be a problem. After doing some reading, I discovered that agents with continuous action spaces can be notoriously difficult to train. And we also have the issue of the potentially long latency step times during that training. I still want to prove that we can deploy an RL agent to a microcontroller, so for now, I think it's best I limit the scope of this project. Discrete action spaces are supposedly much easier, so I'm going to try that. And let's start the agent with a much simpler task. Instead of doing a swing up and balance, let's just focus on that swing up part of the problem. We can always come back to full balancing later, although that may require using something other than simple baselines, gymnasium, and serial over USB due to that long step time. The first thing we're going to do is limit our action space. Instead of being some continuous range of values between -60 and +60 degrees, we'll say the agent has only 3 options. Move the stepper -10 degrees, don't move it at all, or move it +10 degrees. The next thing we do is add a goal zone of about ±5 degrees from the top position. If the pendulum is within that zone and moving fairly slowly, say less than about 540 degrees per second, then we assume the agent has completed its job. We'll give an award of +100 points and go ahead and end the episode. Finally, we add what I call a crash zone, as we want to penalize the agent for moving the pendulum too fast. We don't want it whipping around. If the pendulum is within ± about 45 degrees of that top position and moving over 540 degrees per second, then we consider the pendulum to have crashed. We award -200 points and end the episode. Let's implement these changes and see what happens. We'll start a new project in weights and biases since we've made so many changes and begin the trials again. Even after only 10 or 20,000 steps, we see the agent starting to be a little more deliberate in the actions it takes. After a few trials, the agent is most solidly learning, which is great news. It's not perfect, but I think this is plenty good enough to prove our swing up AI. We'll pick the model that performed the best in the latest trial and convert it to the open source Onyx format. From there, we strip out the value network and save it in a new Onyx file. If we open this file in Netron, here's what the exported network looks like. It's just our 3-layer agent without the value network. Notice there are now 3 output values instead of 1. Each output corresponds to the confidence level of one of the actions, -10, 0, or +10 degrees. Whichever output gives us the highest value, that's the action we take. I then use Edge Impulse to convert this Onyx file to a C++ Arduino library. There's a useful feature here where I can give it a test observation and it will give me the 3 output values. In this case, because 0 has the highest value, then the action we would take is to not move the stepper motor at all. This is handy when we go to test the agent operation on the Arduino. Finally, we create our inferencing application. Just like we did before, we get the encoder and stepper angles, calculate the angular velocities, and scale them by 180 degrees. We feed these values into the neural network that we trained, and we find the index of the highest output value. Using that, we determine which action to take, and then tell the stepper motor to perform that action. We check to see if we've landed softly at the top or crashed, and print the appropriate message to the screen. Let's upload this to the ESP32 and see if it works. All right, moment of truth. You got this. You got this. Oh, yes! Okay, it worked. It demonstrated swing up well enough. So every 20 seconds or so, it's just going to repeat that process. Notice that the episode is ending whenever it reaches that top. I think this is pretty fantastic. I'm really excited that this works well enough. Now, we can't get full balancing, but that's going to have to be a project for next time. Oh, it went all the way around 180 degrees and it failed. So let's see if it can do it one more time. Come on. Yes! It did it! In the end, we successfully achieved this vision of running a reinforcement learning agent entirely inside a microcontroller. However, note the absence of the reward. There's no learning happening. But this is a great demonstration of what reinforcement learning can do. Maybe we train in a virtual environment, tweak the AI on real hardware, and then deploy to a low-powered microcontroller. I imagine this is essentially how self-driving cars learn, but we can get even smaller. I imagine robots learning to walk or fly using this method. I'm excited to see where this goes. Good luck and happy hacking!